Welcome to another module in this massive open online course. So, we are looking at sampling and we have looked at multiplying by an impulse train, which we termed as ideal sampling. In this module, let us start looking at a different technique for sampling, which is termed as pulse amplitude modulation. Alright. So, we want to start looking at a different technique for sampling, which is basically your pulse amplitude pulse amplitude modulation, that is pulse amplitude modulation, which is PAM. Okay. So, we want to look at pulse amplitude modulation. So far we have looked at sampling in which we have a signal, correct, and that is sampled using an impulse train, correct, using a train of impulses where each impulse is at a multiple NTS and the impulse is scaled by the sample, the value of the signal at NTS. So, we have this impulse for instance at 0, this is scaled by m of 0, this is impulse at Ts which is scaled by m of Ts, this is at 2 Ts which is scaled by m of 2 Ts, minus Ts which is scaled by m of minus Ts, this is m of minus 2 Ts at minus 2 Ts and so on. So, this is your basically impulse ideal sampling. Okay. Or basically impulse based sampling. Now, what we want to do now is we want to generate, rather than using impulses, we want to consider pulses. So, we still have pulses. So, we are sampling still at every NTS. So, our sampling frequency, so let us say we have this signal, and rather than having impulses we have a pulse. So, for instance at 0 we have a pulse of height m0 and duration t. At Ts we have another pulse of duration t and height mts. At 2 Ts we have another pulse, this is at 2 Ts, this is naturally 2 Ts plus t, we have another pulse of height 2 Ts. Similarly, at minus Ts we have a pulse which is minus Ts, from minus Ts to minus Ts plus t, this is of height m of minus Ts. So, what you can see is basically at every, so we still have pulses at each multiple of NTS. So, rather than using impulses, we are using pulses of duration t. So, we are sampling by pulses. So, this is basically sampling using pulses of duration t rather than using pulses, right, not impulses, using pulses of duration t at each NTS. So, the sampling frequency is the same, sampling frequency is still your, the sampling frequency is Fs, the sampling time equals, or sampling interval equals Ts equals 1 over Fs. So, this is still the same, but rather than using impulses we are using pulses. And what are we do? We have the pulse at every nts. So, the nth pulse is from nts to nts plus t. So, the pulse is of duration t, alright, and the height of the pulse corresponds to the sample, or corresponds to the sample value, or corresponds to the signal value at m of nts. So, each pulse is the nth pulse is from nts to nts plus t, correct. And basically what is happening, and the amplitude of the pulse equals value of signal at m nts, amplitude of the pulse, amplitude of pulse at nts is basically the value, amplitude of the pulse at nts is the value of the signal at mts. Okay. So, that is what we have, and you can clearly see basically what we are doing is we are sampling the signal. You can also see that you are sampling the signal at each nts and holding for duration, that is the pulse duration t. So, what we are doing is we are basically sampling at each nts and we are holding that sampling value constant. Previously it was simply an impulse which was momentary, it was just for that instant nts. Now, we are sampling at each nts and holding it constant for a duration t, which is the duration of the pulse. Therefore, we are sampling at each nts and holding the sample value constant for duration t. So, we are sampling it and holding it, and therefore, this is also termed as a sample and hold operation. So, this is also termed as a sample and hold. Okay. So, what we are doing is we are sampling and we are holding it for a duration t, and you can see this duration of pulse t is much less than Ts. So, we have t which is our pulse duration, this is our pulse duration, and Ts is basically your sampling interval. And Ts is basically the sampling interval, and what we desire is we desire that T is much less than Ts. So, we would like to have this quantity T to be much less than, much smaller than the sampling interval Ts. So, this duration of the pulse, this pulse duration T should be much smaller than, T should be much smaller than the sampling. So, the pulse is confined to a relatively small portion of the sampling interval, and the smaller the duration of the pulse, the more precise your sampling is, alright. So, the pulse is simply spreading, it is a sample and hold operation. So, it is basically spreading, it is spreading the value of the signal over the duration of t, alright. And this is also known as pulse amplitude modulation. So, this is also known as flat top sampling because you are employing flat top pulses. So, each pulse is a flat top pulse. So, we are employing flat top pulses. So, this employs what are known as flat top pulses, hence this is also known as flat top sampling. Hence, this is also known as flat top sampling, flat top sampling. Since we are employing flat top pulses, this is also known as flat top sampling. What we are also doing is we are modulating the amplitude of each pulse. Remember, we have a pulse at each NTS that is scaled by the value of the signal at NTS, that is MNTS times the pulse, that is each pulse is of unit amplitude, let us say, and it is scaled by MNTS, that is the value of the signal at MTS. So, this is the pulse whose amplitude is being modulated by the values of the signal at the sampling instances. So, therefore, this is also termed as pulse amplitude modulation. So, you can see that at each NTS, if you look at this, basically what you have is this is the pulse at 0, correct. This is your pulse at TS, MTS, this is your pulse at M2 TS and so on, and also this is your pulse at minus TS and so on. So, what we can see is that amplitude of the pulse at NTS is modulated by signal value at NTS. So, we are taking MNTS, multiplying that by the pulse H, let us say H, our pulse waveform is P shifted by TS. This is your pulse which is shifted to NTS. So, we are taking the pulse, shifting it to NTS, modulating it or multiplying it by the value of the signal at NTS, that is M of NTS, that is what we are doing. So, this is also termed as pulse amplitude modulation. This is also termed as pulse amplitude modulation and simply denoted by PAM, pulse amplitude modulation. Okay. So, PAM stands for pulse PAM also stands for pulse amplitude modulation. And it is also, so this is known by 3 names, basically what we have seen, it is known as basically sample and hold, right, sample and hold type of sampling, flat top sampling, or also pulse amplitude modulation. Alright. The sampling frequency is the same, Fs, sampling duration, that is the interval between the samples, consecutive samples is same, that is Ts, which is 1 over Fs. The sample is now is not an impulse anymore, it is of finite duration T, right, capital T, which is much smaller than Ts, which we expect to be much smaller, which practically should be much smaller than the sampling interval Ts. Okay. Alright. So, that is basically your pulse amplitude modulation, where we are sampling using rectangular pulses, and the amplitude of each pulse at NTS is modulated by the value of the signal, that is MNTS at the sampling instant MNTS. Okay. Now, if we look at the pulse as we have already seen is basically the pulse as we have already seen is basically it is basically of height 1 of duration t. So, this is my pulse. Let us say we denote it by Pt equals it has duration at equal to 1. I can represent this pulse as 1 if 0 less than equal to t less than equal to 1 and 0 otherwise. This is my pulse that I am using for, I am sorry, 0 less than height 1 and duration of capital T and height equals 1, and this is less than equal to 1 if 0 is less than equal to t and 0 otherwise. And now what you are seeing is at the mth sampling time we have at mth sample or at nth sample we have you have m of NTS sample at n times the sampling instant multiplied by the pulse shifted by NTS, correct. This is the pulse shifted by NTS. This is your sample at or signal value at NTS. This is your pulse shifted by NTS. So, you have each sampling instant you have the pulse, you are shifting the pulse, scaling it by the amplitude of the signal at the sampling instant, alright. And this we are doing, see, this is similar to the impulse sampling, where instead of where previously in the impulse or ideal sampling we have the impulse, alright, impulse shifted to every NTS and its impulse scaled by MNTS. Now, instead of the impulse we have the pulse. So, the pulse shifted to NTS. Okay. So, what we have here is basically pulse shifted to NTS scaled by MTS and then the sum of all these pulses, that is our pulse stream. So, our pulse stream or pulse amplitude modulated stream is basically n equal to minus infinity m of NTS p of t minus NTS. This is our, let us say this we call it as our m f of or m p of t, which is our pulse amplitude modulated stream. This is our pulse amplitude modulated stream. This is our pulse amplitude modulated stream. Pulse amplitude modulated stream or basically pulse amplitude modulated or PAM signal, or you can also call it as a pulse amplitude modulated, you can also call it as a pulse amplitude modulated signal. This is our PAM signal, which basically a stream of pulses, amplitude at each stream of pulses, each pulse at every NTS that is nth multiple of Ts, and its amplitude scaled by m of nTs. This is the stream, alright, summation n equal to minus infinity to infinity m of nTs times p of t minus nTs, where previously we had a modulated, that is scaled impulse train, alright, a train of impulses, impulse at every nTs with scaled by m of nTs. Now we have pulse at every nTs scaled by m of nTs. And naturally this can be expressed as, now if you look at it, you can think of this as basically at every Ts, correct, at every nTs. You can think of this as the original, your original impulse stream convolved with the pulse, because we have our original stream of impulses, correct. Remember, we have our original stream of impulses, correct, at Ts minus Ts and so on. We have original stream of impulses 0 to Ts minus Ts minus 2 Ts, and now what we are doing, in addition we can convolve it with a, I can convolve it with a pulse, correct. So, if I convolve it with a pulse, this impulse stream, if I convolve it with the pulse, will give me, so I have the impulse stream or impulse sample stream. I can represent it as impulse sample stream convolved with your pulse, that is Pt. So, our impulse sample stream or impulse sampled signal is, remember, m delta t equals, well, summation n equal to minus infinity to infinity m of n Ts into delta t minus n Ts, okay. Okay. Now, this is basically the convolution operator. The star represents convolution. Now, I take this m delta t, correct, m delta t, and convolve it, okay. Take this m delta t, convolve it with p of t, that is basically my, substituting for m delta t, that is basically my summation of n equal to minus infinity to infinity m of nTs into delta t minus nTs convolved with p of t. So, that basically gives me summation n equal to minus infinity to infinity m of nTs delta t minus nTs convolved with pt, that is basically p of t minus nTs, which is nothing but my mp of t, that is nothing but my pulse amplitude modulated signal. So, this signal, which is basically m of nTs p of t minus nTs summation n equal to minus infinity to infinity m of Ts nTs into p of t minus nTs, this is basically my pulse amplitude modulated signal. This is my or this is basically my PAM. This is basically my pulse amplitude modulated signal or basically my PAM signal. Okay. So, therefore, we have derived the expression for the PAM signal. What we are saying is, so what we have seen is that basically rather than ideal sampling, of course, which is difficult to implement because one has to generate impulses, a train of impulses, and train of impulses is impractical right, is impractical to generate. So, one can replace them by pulses which are more realistic. A pulse which has a finite amplitude and finite duration, alright, a pulse of a certain height which has a finite duration, much lower than the sampling duration, or we desire it to be as low, much lower than the sampling interval, that is the pulse of width capital T, which is much less than the sampling duration, sampling interval Ts, alright. And therefore, now one can sample the signal at each Ts multiple or each NTS and hold it for a duration of T, which is the duration of the pulse, alright. This is known as flat top sampling, or also known as a sample and hold, and this can be represented as analytically it can be represented as the convolution of the original impulse sampled signal, although it is not the operation that we are performing. It is not that the signal is the pulse amplitude modulated signal is being generated by first impulse sampling and followed by passing through a filter with response given by the pulse shape, rather it is simply a representation. So, this flat top sampling operation can be analytically represented as basically sampling or impulse sampling the original message signal MT, followed by passing through a filter with impulse response given by the pulse shape PT, alright. So, that gives us basically the stream of pulses each shifted to each NTS and scaled by the amplitude or the value MNTS of the signal at the nth sampling instant. So, this is the pulse amplitude modulated signal, and subsequently we look at the frequency response and also how to reconstruct the original signal from this pulse amplitude modulated signal. Thank you.